Hello. In this video I'd like to talk about polyprotic acids as described in chapter 14.7. Up till now in this unit we have mainly been dealing with what are called monoprotic acids, and as the name implies, a monoprotic acid is an acid that is capable of donating only one hydrogen ion per acid molecule. And there's an equation that shows the equilibrium ionization of a monoprotic acid HA to form 1 mole of H plus 1 mole of A minus. And we can write the Ka expression, as we always have. Ka equals the product of the hydrogen ion concentration and the conjugate base concentration divided by the concentration of the remaining unionized acid. A polyprotic acid, on the other hand, is an acid that is capable of donating more than one hydrogen ion per molecule of acid. If it's 2 hydrogen ions, it's a diprotic acid. If it's 3 hydrogen ions, it's a triprotic acid, and so on and so forth. And let's look at what those look like. I'll represent a diprotic acid as H2A, and here it shows it in equilibrium with a hydrogen ion and HA minus. HA minus is the conjugate base of H2A. Notice again, the charge on the conjugate base is 1 less than the charge on the acid because it has lost hydrogen as the hydrogen ion H plus. And I can write the equilibrium expression for the first ionization of this diprotic acid as the concentration of H plus times the concentration of HA minus divided by the concentration of H2A. However, because this is a diprotic acid, there is a second and subsequent ionization. HA minus still has a hydrogen ion capable of being released as H plus, so it does so, forming H plus and A2 minus. A2 minus is the conjugate base of HA minus, and once again, notice that the conjugate base has a charge that is 1 less than that of the parent acid. And I can write the Ka2 expression as H plus times A2 minus divided by the concentration of HA minus. One important point is that the ionizations are successive, not simultaneous, which means they happen one after the other, not at the same time. How do you suppose the subsequent Ka values vary? In this example, how do you think Ka2, the numerical value of Ka2, compares to the numerical value of Ka1? Well, as you might guess, Ka2 is always less than Ka1, and that's because HA minus has a negative charge. Therefore, it is holding on to the proton more tightly by a greater electrostatic attraction. Therefore, it is less likely to ionize. And we'll see examples of that. So let's do an example problem. Calculate the pH, percent ionization, and equilibrium concentrations of all species present in a 1 molar solution of the diprotic acid malonic acid. Now I give the complete formula of this organic dicarboxylic acid here. Let's look at the structure just out of curiosity. I have a carboxyl group at one end of the molecule. I have a CH2 group in the middle, and I have another carboxyl group at the other end of the molecule. And remember, in carboxylic acids, it's only the hydrogen on the carboxyl group that comes off as H plus. The 2 hydrogens on the middle carbon are not acidic in water. For simplicity, I'm just going to represent this as H2A so I don't have to write the equation out all the time. So let's consider our subsequent ionizations. H2A in equilibrium with H plus HA minus. For malonic acid, pKa1 equals, forgive me, let me write the equilibrium expression as well, just so we have that. So Ka1 equals the hydrogen ion concentration times HA divided by H2A. I'm going to express the equilibrium constant. pKa1 is 2.83. Now, what does pK mean? Well, just as pH means negative logarithm of the hydrogen ion concentration, pKa means the negative base 10 logarithm of the Ka. That's a way that you see equilibrium constants for weak acid ionizations, frequently denoted, so please be aware of this. So that means that Ka1, Ka1 equals 10 to the negative pKa1 equals 10 to the negative 2.83, or 1.5 times 10 to the negative third. Now, for the second ionization, HA minus is in equilibrium with H plus A2 minus. Ka2 is H plus A2 minus over HA minus. move all this out of the way. And pKa, sorry, that should be pKa2 equals 5.69. So Ka2 is 10 to the negative 5.69, or 2.0 times 10 to the negative 6th. So we have equations to represent the subsequent ionizations, and we have equilibrium expressions for the first and second ionizations, and we have numerical values of the ionization constants. So we are going to treat each successive ionization sequentially. The important point is that the products of the prior ionizations become the reactants of the subsequent ionizations. So let's see how that works. So here's the equation to represent my first ionization. As always, I'll set up an ice table. My initial concentration of the diprotic acid is 1 molar. My initial concentration of the hydrogen ion is approximately 0 molar. My initial concentration of the conjugate base, Ha- is 0. I'll call the changes in concentration minus x plus x plus x. That gives me 1.0 minus x, and x. Ka1 is equal to H plus Ha minus over H2A equals x squared over 1.0 minus x equals 1.5 times 10 to the negative third. I'll make the simplifying approximation that x is much smaller than 1 molar, and that gives me x equals the square root of 1.0 times 1.5 times 10 to the negative third is equal to 0.039 moles per liter, equals the hydrogen ion concentration from the first ionization, as well as the equilibrium concentration of Ha minus. My concentration of H2A that remains is the initial concentration minus the decrease, 0.039 molar, or 0.96 molar as my concentration of H2A, and the percent ionization is 0.039 molar over 1.0 molar times 100, or 3.9% ionization. So let's draw boxes around our results. Now, I haven't calculated the pH yet, because that raises the question, is this first ionization the only significant source of H+, or does the second ionization also contribute to the equilibrium concentration of the hydrogen ion? Well, let's look and see. From the first ionization, we have our initial concentrations of the hydrogen ion and Ha minus, 0.039, 0.039. Do not make the mistake of assuming that the initial hydrogen ion concentration in the second ionization process is equal to 0. It's not. It's what was produced in the first ionization. But my initial concentration of A2 minus is, of course, equal to 0, minus x plus x plus x, 0.039 minus x, 0.039 plus x, and x. So for my Ka2 expression, I can write H plus A2 minus over Ha minus equals 0.039 plus x, 0.039 minus x, which we said was numerically equal to 2.0 times 10 to the negative sixth. That's a small enough equilibrium constant that I'm going to assume that x is negligible in comparison with 0.039. So I will cancel it. 0.039 clearly cancels as well. And I get that x is equal to the concentration of A2 minus, which is equal to 2.0 times 10 to the negative sixth molar. Okay. Now, it's almost always the case that the first ionization is the only one that produces a significant concentration of hydrogen ion. There are exceptions, which we'll talk about in a second. Why would that be? Well, essentially, you can think of this in terms of Le Chatelier's principle. Okay? If we have a substantial concentration of hydrogen ion produced by the initial ionization, that will suppress the subsequent ionization, pushing the equilibrium back towards the reactants Ha minus. Therefore, any subsequent ionization is going to be small. So here are the summary of our results. Our remaining concentration of the diprotic acid, malonic acid, is 0.96 molar. Our equilibrium concentration of the hydrogen ion and HA- is 0.039 molar. Again, the second ionization did not produce a substantial concentration of H+. pH is 1.41. Concentration of the conjugate base is 2.0 times 10 to the negative sixth, and it's 3.9% ionization. Okay, now, I asked previously, is the first ionization always the only significant source of H+? And I will answer that by saying, usually, but not always. And of course, I'm going to give an example of when it's not the only significant source of H+. So let's consider sulfuric acid. Sulfuric acid is very unusual in that it is a diprotic acid. The first ionization is a strong acid ionization. So for the first ionization of H2SO4, as I've shown in the first equation, Ka1 is so large that we don't measure it. We assume that H2SO4 is completely ionized to form H+ plus HSO4 minus, the hydrogen sulfate anion. The second ionization, the ionization of the hydrogen sulfate anion into the hydrogen ion and the sulfate anion, is a weak acid ionization, but 0.012 is a pretty large equilibrium constant for weak acid ionization. So let's calculate the pH of a 1 molar solution of sulfuric acid. Well, from the first ionization, which we assume goes to completion, the hydrogen ion concentration equals the equilibrium concentration of the hydrogen sulfate ion is equal to 1.0 molar, and that's because the equilibrium concentration of sulfuric acid is equal to 0. Remember, it's a strong acid, so it's completely ionized. Now, for the second ionization, we are starting with the 1 molar hydrogen sulfate concentration as a result of the first ionization. So I'll take my hydrogen sulfate concentration, H plus SO42 minus, set up my ice table, 1.0, 1.00, minus x, plus x, plus x, 1.0 minus x, 1.0 plus x, x. Ka2 is equal to the concentration of the hydrogen ion from the second ionization times the concentration of the sulfate anion divided by the equilibrium concentration of the hydrogen sulfide anion, which is 1.0 plus x times x over 1.0 minus x, which is equal to 0.012. Well, we can see that if we assume x is negligible in comparison with 1.0 and cancel it, we will simply get the value of x equal to 0.012, which is clearly less than 5% of 1.0. So the simplifying approximation is valid, and that gives me that the sulfate ion concentration is equal to x equals to 0.012 molar. And my hydrogen ion concentration is equal to the 1 molar concentration from the first ionization plus the 0.012 molar from the second, which to significant figures is simply equal to 1.0 molar as my hydrogen ion concentration. And my hydrogen sulfate concentration is equal to the 1.0 molar from the first ionization minus the 0.012 molar from the second ionization, or again, 1.0 molar is my hydrogen sulfate concentration, and my pH is equal to the negative base 10 logarithm of the hydrogen ion concentration, or 0.00 as my pH. So here are our results. Sulfate concentration, hydrogen ion and hydrogen sulfate concentration, and my pH. In this particular case, because we started with 1 molar sulfuric acid, the initial hydrogen ion produced by the second ionization is negligible. But what if we start with a much more dilute solution of sulfuric acid? We saw earlier in the unit that as you increase the dilution of the concentration of an acid, the percent ionization increases by Le Chatelier's principle. So let's check this out. So for the first ionization, again, doesn't matter. The first ionization of sulfuric acid is a strong acid ionization, so we assume that it goes to completion, which means that my hydrogen ion concentration and hydrogen sulfate concentration from the first ionization are equal to 0.0100 moles per liter. For the second ionization, which is governed by Ka2, 0.012 molar, let's set up our ice table. Hydrogen sulfate ion, the hydrogen ion, and the sulfate anion. I've got 0.0100, 0.0100, and 0, minus x, plus x, plus x, 0.0100 minus x, 0.0100 plus x, and x. When I plug these into the Ka2 expression, Ka2 is the hydrogen ion concentration times the sulfate concentration divided by the hydrogen sulfate concentration. I get 0.0100 plus x times x divided by 0.0100 minus x equals Ka2, which is 0.012. Now, you may be tempted at this point to say, oh, I'll make the simplifying approximation. I will cancel x relative to 0.01. Well, if you do that, you will see pretty quickly that you will get a value of x equal to 0.012, which is not only not negligible in comparison with the initial concentration, it's greater than the initial concentration. So that clearly doesn't work. So what you will have to do in this case is use the quadratic or the online polynomial solver, which will give you a value of x equal to 0.0045 molar. Okay? So now my hydrogen ion concentration is equal to the sum of the 0.001 molar hydrogen ion concentration produced in the first ionization plus the 0.0045 molar hydrogen ion concentration produced in the second ionization, which, because we began with a much more dilute solution of sulfuric acid, is not negligible, to give me 0.0145 molar as my hydrogen ion concentration, from which I can calculate the pH. The pH equals negative base 10 logarithm of 0.0145, which is equal to 1.84 as my pH. Okay? Again, this is higher than in the previous case because we were starting with a lower initial concentration of sulfuric acid. So even though we got non-negligible amounts of hydrogen ion from both ionizations, the total concentration is still less. Okay, that's what I want to say about diprotic acids. And in our next video, we'll talk about the acid-base properties of salts. See you then.